like people are slowly filtering in. So we might as well just kick things off, and I'll go through a bit of housekeeping first, if that's okay. Just to let everyone know, we are recording this webinar as we usually do, and we will be making it available for you likely tomorrow. We'll send that out. So if anyone needs to leave early, feel free, we'll send this out later. And if you have questions throughout, you can use the Q&A function, so you don't forget a question later. You can use it now, or the chat function, and then during the Q&A, I'll be kind of asking Ross and Mike questions later. But before we kick things off, I'd like to acknowledge that this meeting is being held on the traditional lands of the Wurundjeri people of the Kulin Nation, and pay my respect to elders, both past, present, and future. All right, so I would like to introduce Ross George, who's the CEO of AUSTENG, a facility in Geelong. And AUSTENG is an advanced manufacturing company, and they're a strategic partner and major investor in Capricorn Power, and are currently commissioning our Mark II heat engine. Hello, Ross. Thanks for joining us today.
That's a pleasure, Saujanya. Hello.
Hello. So thanks again for joining us and for making yourself available for the chat today. I just wanted to discuss the use of the Barton heat engine at a combined sludge and FOGO, which means food organic and green organics, treatment plant in Victoria. And that's kind of the reason that we're chatting today. So I might as well kick off with the first question. Can you tell us a little bit about the combined sludge FOGO plant application that you've been looking at, and how the Barton heat engine fits into this? And actually, I believe I have a diagram from you that sent over. So if you don't mind, if everyone doesn't mind, I'll just share my screen. That might help.
So while you're doing that, the plant that's being looked at is treating food organics, garden organics, but one of the interesting parts of it is that they've got a hydrocarbon sludge that they also want to process, which requires high temperature drying, and so that's one of the unique parts about this particular application. The process, the reason we're drying the FOGO and the sludge is to put through a pyrolysis machine. The combustion of the syngas produces high temperature heat. So what we're able to do is actually take all of that heat, and that's the important part of it. We're able to take all of that heat and put it through the Barton engine. So we can, and with the Barton efficiencies that we're looking at, we can generate the thermodynamic efficiencies. We can generate substantial amounts of electricity. But, and this is the really good part, the way the engine is configured, or the way we can configure it for this application using recuperation, allows us to pass a lot of the heat through, so we can then use it for the high temperature drying. So we're taking in high grade heat, we're generating power from that, but we're also rejecting the heat still at, albeit at a lesser temperature, but at a it's still reasonably high grade, suitable for this high temperature drying application, which is what that diagram there shows. So we're passing, we're able to use more than or half the heat for the drying application, even after we've generated electricity.
Yeah, great. And I'll just stop my share really quick.
Yep.
So that kind of brings me to my next question of, why is the Barton heat engine configuration better than the alternatives? And one more diagram that Ross has sent over, just a quick share again. All right, thanks for bearing with me.
Yeah, so so this is one of the alternatives that was initially proposed, was using Organic Rankine. The Organic Rankine, in general terms, accepts heat at a lot lower temperature. So what the the alternative flow diagram was that they actually had to split the high temperature heat source. They needed at least 50% of the high temperature heat for the drying process, which only left 50% of the heat for putting through the organic Rankine. And to get it through the organic Rankine, they had to dilute it down to a lower temperature and then do the energy conversion there. The nature of these engines are such that the conversion efficiencies aren't quite as high. So instead of, we produced of the 100% of the heat available from the heat source, the Barton engine scenario was able to generate, convert that about 30% of that into electrical power. This scenario was only about 6%. So it was a pretty fantastic outcome that by configuring the Barton engine in the right way, we could generate 5 times more electricity from the same bucket full of heat energy, which is a great outcome for both the end customer and the environment.
Yeah, absolutely. Just stop the share again. And so, I'm just trying to contextualize this for everyone. So what are the feedstock that's used and what are the outputs?
So the feedstock is food organics and garden organics. So it's the normal material you'd see. So it's branches, it's food waste, it's it's all that sort of stuff. The interesting part of this is the other hydrocarbon sludge that's coming in was the unique part in that it required high temperatures to dry it out. So and the outputs are electricity and biochar through the pyrolysis. So it's a it's a carbon capture and an energy production.
Great. And can you kind of give us some statistics around this process?
It's interesting. So the design point is we're taking 85 tonne per day of the organics, and that's converts into 30 tonne per day of dry material. So it's quite a significant materials handling process, and we're taking, if you do the maths, we're taking 55 tonne of water per day out of that material to have it suitable for pyrolysis. It's interesting. It's not wet enough for anaerobic digesting. It's very wet. We need to dry it for the pyrolysis. And using the Capricorn Power Barton engine technology, we can use the heat rejected from the Barton engine to actually do that drying. And as I said, we're removing 55 tonne of water a day.
Yeah, great. And obviously this big process, what are the tasks that have to be done with this?
Oh, so it's a materials handling exercise, but from a thermodynamic point of view, we've got to dry this material. We've then got to pyrolysize the material, and from that pyrolysis comes the syngas, which we can then combust to get the high temperature heat source, which we can then use to generate electricity through the Barton engine, and then what's left over of that goes back into the drying. So it's a circular path. So the tasks are drying, pyrolysis, and electricity generation.
Okay. So I found this pretty fascinating. What is the incoming temperature?
So the temperature of any combustion in syngas is, of the order of that 800 degrees, 850, where the Barton engine in its current configuration accepts heat at 450. But it rejects heat. The important part is if we configure it for this particular application, we're taking it in at 450, but we're rejecting the heat at 300 degrees, and we can do that because of the recuperation. So the recuperation is such that we're using the useful heat inside the closed loop. We can capture the heat from the expander, use it to preheat the incoming, which means we can reject heat at a much higher temperature. And while that sounds a bit engineering, the beauty of it is we've got really, really good high value heat that you can use for other processes, which, to the best of my understanding, all the alternatives don't have that luxury. So we've got this sort of fantastic option with this technology to use the reject heat for anything we can think of.
Yeah, and I think that was really interesting for me to learn about the kind of the value of heat and how different applications, or that it applies to different applications.
Yeah.
So is there any use for waste heat?
Well, the use, it's at 300 degrees, so it's really, really, really useful. You know, we're using it in this, or proposing to use it in this process for high temperature drying. But really, the world's your oyster in this, because so you can, I mean, just off the top of my head, through a heat exchanger, you could use it for baking or cooking or things like that. You can use it for steam generation, high temperature, high pressure water. You could even snuggle an organic Rankine cycle machine in there to actually suck a little bit more electricity out of the heat. Sterilisation, chemical processing. Even if the temperature is not high enough for a particular application, 300 degrees, you can use it for preheating. And if you go down that track, I just did a quick. You do a quick look on Google, and Arena quotes that 22% of the nation's energy use is in industrial heating. Now, if we can take our reject heat and use it in industrial heating, we're making huge savings apart from or added to the electricity generation. It's an enormous opportunity.
Yeah. And so I think, like, you know, the reason why we're having this webinar today, if you could explain like why this is so exciting for us for Capricorn Power.
Well, it's exciting because it opens up just a whole nother range of opportunities and range of applications to use the Barton engine. Because it's unique amongst all the comparable technologies, and therefore we can apply the Barton engine to a whole lot of other different scenarios that we previously hadn't thought of.
Yeah.
So it potentially expands our market, I suppose, is the simple thing. And you know, and from an environmental point of view, if we can capture this waste heat and use it, it's a better environmental outcome apart from the commercial outcome for Capricorn Power. Yeah,
that's great. So how did our findings in this specific case exceed our expectations?
Yeah, well, see, I mean, you know, I've been in this sort of paradigm that, okay, we've got a better thermodynamic, Capricorn Power's got a better thermodynamic efficiency than the alternatives. So, you know, we're saying that we can generate 50% more energy from the same bucket full of heat. We can generate maybe 100% more from the same bucket full of heat. So I thought we were in that, you know, sort of 1.5 to 2 times, maybe a little bit more paradigm. But what this really uncovers is the fact that because we're rejecting heat at a higher temperature, and we can accept heat at a higher temperature, and we can pass all of that heat through our engine, we can then capture a lot more of that energy. And so, so it's if we design the engine for the right application, so it's the right technology for the right application, you know, it far exceeds the 1.5 times or the 2 times, and this demonstration shows, you know, we can just get so much more output.
Great. And so most people, we assume that the client or the customer wants to generate renewable electricity energy, and that ideally this would be firmed or dispatchable on demand.
Yeah. So look, I think one of the opportunities we've got here is it actually doesn't necessarily have to be firm. It doesn't have to be baseload power. Pyrolysis, my understanding is you can turn that up and down. So so we've got some opportunities there. So potentially with this, we can. It seems to me we can achieve the holy grail of renewable, dispatchable, carbon positive energy, because the carbon positive comes from the pyrolysis. We're going to generate biochar, which we can then capture. in various forms. Soil carbon's the most common one. If we can turn our pyrolysis machine up and down, we can make it dispatchable. So, at peak times, we can put more material in our pyrolysis equipment, generate more syngas and generate more electricity. We've also got an option in Capricorn Power, which is not the topic of this discussion, but we can also store in thermal storage to make it dispatchable. So this sort of scenario offers us, the wonderful opportunity of the three dispatchable, renewable, carbon capture, holy grail.
Yeah, that is really exciting.
Yeah.
And can you tell me what, again, it really helped me to contextualize this scenario. Can you tell me what would traditionally be used in the market for the heat to electricity application in a circumstance like this?
Well, traditionally what had happened, Saujanya, is this material is going to landfill. So it's just filling up landfill and creating methane. And okay, we're burning the methane and turning it into carbon dioxide, but we're not doing anything useful with it. So at the minute we're clogging up landfill and creating CO2. What this does is just awesome in that it captures the carbon, it gives us an absolute bucket full of electricity, and it's not going into landfill, and it's not creating as much CO2. So it's a real win-win. Yeah,
that was the coolest part for me. So the Barton is the Barton heat engine a good engine to use in this application? And if so, why? Especially compared to other tech,
But my understanding is it's the only engine you use in this application, because the alternatives reject heat at a lower temperature that you can't use for these other higher temperature applications, they're not as efficient at generating electricity. So it's I think Capricorn Power have really landed on an absolute winner here, because of the temperatures and because of the thermodynamic efficiencies.
Yeah, great. And I guess, are there other applications that you think this could apply to?
Well, again, I think the challenge for Capricorn Power is to go out and find customers that need that not only need electricity, but I think the potential is there. If you've got customers that need electricity and reasonably high grade heat, they'd be crazy not buying this, because it ticks all of those boxes. So yeah, well, I mean, I think I mentioned a few applications before. There's anything that needs heat at these sorts of temperatures is a possible user.
Yeah, and so my last question before we move on to the Q&A. What does that mean for the future of the Barton heat engine in applications like this?
Well, it means the future is, I think, a much wider market than we originally thought. Much wider. And I think it's potentially good for Capricorn Power's customers, because they're going to get more revenue out of it. It's good for Capricorn Power because it opens up more markets. It's good for the environment because we're capturing more. We're making use of the energy that's there, rather than wasting it and blowing it off on something that's less efficient.
Yeah, great. Thank you for that. And I think before we head to the Q&A, I might get our CEO, Mike Hodgkinson, to join us for the Q&A. Just need to find him. There we go. All right. So again, for anyone, if they join late, feel free to use the Q&A or the chat function to pop in any questions you might have. So the first question I have is, hi, Mike. Hey, how are you? So the first question I have is the high grade heat input? Oh, that's kind of a half answer. Maybe I didn't quite answer. If you wrote that question, if you could clarify, that'd be great. Otherwise, I'll move to the next one. So somebody thinks they missed it. What are we using the heat to dry? Is it organic material?
So yeah, so the material for this is organic material. It varies from food to organics to this other sludge. The sludge is organic.
Okay.
So that's why it goes into the pyrolysis, because it is an organic material, so it will pyrolyse.
And there's actually a follow-on to that. They said, and if so, what does the drying process allow for? What can you do with the substance once it is dry?
So once it's dry, we're putting the whole lot into pyrolysis. So it's a continuous pyrolysis machine. I'm not sure that the end customer's chosen which pyrolysis technology they're using. But from a Capricorn Power point of view, because we're agnostic to the heat source, we can process whatever comes out of whatever machine.
Great. And I have a couple questions it's the same question from a couple of people. Can you explain the original heat source and more about the high heat source?
So, well, I mean, you asked before, Saujanya, about what would traditionally happen, and I said it'd go into landfill. The other alternative is you dry it and you combust it. And that would drive a heat engine, and that'd be fine. But there's no carbon capture step in that. So it could be dispatchable. It's certainly renewable, but it's not carbon positive. So the way they're intending to do this makes it carbon positive as well. Does that answer the question?
I hope so. I think so. You can get follow-ups from the audience if there are more. And the next is, how clean does the waste gas heating stream have to be before it can be fed into the Barton heating?
Ah, what a great question. And the answer is it doesn't have to be clean at all, because we're not an internal combustion engine, we're external combustion. You can throw any amount of crap at it. And all you have to do every now and again is clean the heat exchangers. So it can be relatively dirty gas. So separate to this discussion, it can be tip gas. Anything that's horrible will run the engine. It's absolutely completely agnostic.
Right. And then I have a couple of questions around pyrolysis. I'll just kind of ask you at the same time. Somebody's asking what pyrolysis is, and then how does the pyrolysis start up from cold? And then does the syngas come from the pyrolysis?
Cool. So it'd be better to run it 24/7. It'd be more efficient. The way you start it up from cold is you do need to apply an external heat source to get it up and running. Once it's running, it's self-sustaining. So again, depending on the technology and depending on how wet the product is, can take, the ones I've seen take 15, 20 minutes to start up, and they're producing some syngas. And the answer to your next question is the syngas does come from the pyrolysis itself. So it's the pyrolysis is an oxygen deprived environment, so it gasifies the organic material, drives off the gas, and leaves the carbon.
Okay. And someone's asking what the sludge is.
Commercial in confidence.
And that actually leads me to a question for Mike in terms of commercial. Somebody wants to know what companies we're already working with.
Sorry, what's the exact question?
What kinds of companies are we already working with?
Sure. So as Ross mentioned, this is a pyrolysis process. So there are several Australian providers of pyrolysis systems, and we know all of them, and we have varying degrees of relationships with all of them.
And
the great thing about the Barton engine is we don't have to hitch our wagon to any particular technology. They all produce heat, and we can couple to any of them, and we don't even need to couple to them full time. So it's a very universal technology.
And the next question is, what happens to the vapor that comes off the drying? Could there be an issue with toxic emissions?
So the food organics and garden organics, we're just driving off water, and you'll get some. I mean, if you're drying eucalyptus plants, you're obviously going to get some eucalyptus vapors and whatnot. But the food organics and garden organics are benign. The sludge, the fume that comes off that, we're actually putting back through the combustor. So we're effectively using the combustor also as an afterburner. So we're quite comfortable. In fact, very comfortable. The emissions coming out of that are going to be very clean.
I think the next question could be for Mike or Ross. How scalable is the engine? I.e., is there a maximum kilowatt size that can be containerized? And thereafter, is it scaled in a modular fashion to achieve higher kilowatt outputs?
Your answer, Mike.
Okay, great. Yes, so there will be a physical limit, obviously, to the megawatts that we can fit into a container, but that will improve that over time because we've found that customers really want that containerized, transportable heat engine solution. We could probably build about 400 kilowatts, in the extra long or wide 40-foot container at the moment. But there are many pathways to increase the power density ahead of us.
Great. This next question might also be for you, Mike, but happy for us to go for it. Was this an application that Capricorn Power expected to be possible, or is it something that has been discovered during the development?
So this application was only discovered recently. So that's why we held the webinar to shout out to everyone about this discovery. Because it is a big deal. That just to highlight Ross's point, we were claiming up to 3 times the efficiency of with the Barton engine. So a 30% efficiency versus 9 to 15% efficiency for Organic Rankine Cycle, and of course we have a pathway up to as close as we can get to sort of the theoretical efficiency of 60% at 600 degrees Celsius. So we've got a pathway up well above 30% and therefore well above the up to 3 times claim. But what happened just recently with Ross's engineering consulting to another commercial in confidence organisation is this discovery, which almost doubles the electricity generation in this particular use case, and it's a pretty significant use case. Mm. So we're very happy. It definitely means that we will be thinking very carefully about target markets that are relevant for this use case, because we've just doubled our commercial advantage virtually.
Yep. I thought I'd let you take that one. And is there opportunity use in end-of-line communities?
Yes, so bioenergy or solar thermal power stations at the end of the grid, is a great application, because instead of a massively expensive grid upgrade exercise, you've got continual sustainable renewable electricity generation to match the electricity load at the end of the grid.
Yeah, great. I think we might just stick to maybe 2 or 3 questions to make sure everyone can get to dinner on time. So the next one is how scalable is the engine? Oh yeah, we already did that one. Sorry. Your views about the Barton engine application when compared with traditional combustion of biomass, such as rice husks, and generate power using steam turbine.
Yes, so the problem with steam Rankine cycle is it's got two big problems. The first is it uses a lot of water, and we think that's unsustainable, the amount of water that steam Rankine cycle uses. And the second is it doesn't really scale down well. So it's well known in these sort of 100 megawatt power station plus scale, but once you get down to sort of 10 megawatts or lower, it becomes quite efficient. It's quite inefficient, I should say. It's quite difficult to manage. And so it's not really a competitive to us at that sort of scale. That's why Organic Rankine Cycle was used, for example, by the other engineering company in this use case that we talked about.
Yep. And someone said that it sounds impressive. What is the estimated total market and GHG reduction? What happens to that currently?
Yeah, so we'll have to look, as I mentioned, we just sort of made this discovery. We'll have to look carefully at the market with these, 300 degrees Celsius heat uses, industrial heat uses, and do that market calculation.
And we kind of have a fun question at the end. Are there any other happy surprises in the pipeline?
we do have many, well, I should say several opportunities, but until we finalise them, we can't announce them. So that, that's the exciting thing about Capricorn Power. There are lots of great opportunities, and our job is to push the very best ones into closure, and only then can we announce them.
Great. I just want to thank Ross and Mike for joining me today, and thanks for everyone else for attending. I know everyone's lives are very busy, so we really, really appreciate it. If you do have, get off the webinar and you have another question, you can always email us at info@capricornpower.com.au, and we will be sharing this webinar on our social media, so you can follow us there. And I hope everyone has a great night. Thanks, everyone.
Thank you, everyone.
Thanks. Thank you.